Welcome back. Today we begin Chapter 5, the derivative. Chapter 5 is short. We'll only take a look at 5.1, 5.2, 5.3. In 5.1, we see some interesting examples of a function that is differentiable everywhere, but where the derivative is not continuous. In 5.2, we tackle the official definition of the derivative, and we see some interesting consequences. So recall some basic calculus 1, the derivative. When you look at these two graphs, can you see one of these is a function and the other is its derivative? Which is which? Pause the video if you need to and unpause when you're ready to answer. And f is the solid curve, f prime is the dashed curve. One way that we think about the derivative at a point C is that f prime of C is the slope of the line tangent to f through the point C, f of C. So what about 4, for example? At 4, I go up to the graph f, and I find the point on the graph, and I make a tangent line, and this line has a slope. I don't know, maybe it's a little bit less than 1. Let's say the slope is like about 0.8. So that's the value of the derivative. Right, 0.8. So f prime of 4, for example, is about 0.8. How about some other basic Calc 1 derivatives? The derivative of x squared is 2x. In general, we have the power rule. The derivative of x to the n is n, x to the n minus 1. I can use the power rule to find the derivative of 1 over x, which is negative 1 over x squared. Don't forget the product rule. uv, the derivative of uv is u prime v plus uv prime. And don't forget the chain rule. If I have a composition of functions, the derivative of a composition is the derivative of the outside with the inside unchanged times the derivative of the inside function. So if f is continuous, will f prime be continuous? Think about this. And no. There are some quick examples. So the absolute value is a nice continuous function, but its derivative looks like negative 1 to the left of 0 and positive 1 to the right of 0. So its derivative is not continuous. The cube root of x might seem to be like a little bit more of a natural function. After all, it's algebraic. But here's another example where the derivative doesn't exist at 0. The value of the derivative to the left goes up to infinity. The value of the derivative from the right goes up to infinity. So the derivative doesn't exist at 0. So neither one of these functions is differentiable at 0. The author gives us a nice class of functions where we can explore these things and find some funny examples. So g sub n is x to the n sine of 1 over x when x is not 0, and it's 0 if x equals 0. So we plug 0 in the middle. Now g of 0 is sine of 1 over x. And that's not even continuous at the origin. So certainly if it's not continuous at 0, then it can't be differentiable at 0. How about g1? So this is x sine of 1 over x. And g2 is x squared sine of 1 over x. These things are continuous at 0. But what about differentiable? Are they differentiable at 0? So let's recall our derivative. G prime at a point C is the limit as x goes to C, g of x minus g of C all over x minus C. So how about these guys at 0? G sub n prime at 0. Well, limit as x approaches 0. And what's going to happen with my fraction? G of c equals 0 by definition. G of c equals 0, and c is 0. So this just becomes g of x over x. So in the middle, the derivative of this function at 0, g prime 1 at 0, is the limit as x goes to 0 of sine of 1 over x. Does that exist? No. So g1 is not differentiable at 0. What about g2? At 0, its the limit as x goes to 0, x sine of 1 over x. Sine of 1 over x is bounded by negative 1 and positive 1, but my x goes to 0, and so this whole expression goes to 0. And look at that. The answer is 0. So yes, this function g2 is differentiable at 0, and its derivative equals 0. We're not done with g2 yet. Here's our definition for g2. We just discovered that g2 is differentiable at x equals 0, and its derivative is 0. What about at points not equal to 0? Well, if it's not 0, then I can just use our derivative rules and take the derivative of x squared sine of 1 over x, and I find that that derivative is negative cosine 1 over x plus 2x sine of 1 over x. Now something funny is happening. Do you notice what it is? As x approaches 0 of g prime of 2, that doesn't exist. This cosine of 1 over x doesn't have a value as x goes to 0. So we're in this funny situation where g2 of x is differentiable everywhere, but the derivative is not continuous. So funny things happen when I start looking at differentiability. And so now in section 5.2, we'll get the actual definition and look at some of those consequences. Okay, jumping right in with our definition. Let g be a function from a to the reals. It's a function defined on an interval a. Given a point c in a, the derivative of g at c is defined. G prime of c equals the limit as x goes to c, g of x minus g of c, all over x minus c, provided this limit exists. If the limit doesn't exist, then the derivative doesn't exist. In this case, we say that g is differentiable at c. And if g prime exists for all points c in the interval a, we say g is differentiable on a. Now, this interval a, it might be an open interval that contains c, so x can approach c from both the left and the right. But it's also possible from this definition that c could be one endpoint of a closed or half-closed interval. And that's okay, we still let x approach c, but we always require that x is in a as x approaches c. Well, using this definition, we can now derive some of our basic rules like the power rule. Here's a quick proof of the power rule, just so long as the power n is a natural number. So let c be any arbitrary point in the reals, and here is an algebraic identity. Here's how x to the n minus c to the n factors. Then, by definition, f prime of c is this limit as x goes to c, x to the n minus c to the n over x minus c. And using the above algebraic identity, that becomes the limit of all that stuff. All that stuff is just a polynomial in x. It's a continuous function. So it is continuous at c, so taking the limit as x goes to c, I can just plug in the c for x. And I find I get c to the n minus 1 for every term. How many terms are there? Do you see? There are n terms. So the derivative of f at c is nc raised to the n minus 1. And that's it. That basically proves the power rule. You should contrast that, for example, with the absolute value. What is the derivative of the absolute value at 0? Well, it'll be the limit as x goes to 0, absolute x over x. Can you see why the derivative at 0 doesn't exist? And this shows, by definition, that the absolute value is not differentiable at 0. Now, it's easy to think of a continuous function that is not differentiable, right? Can you think of one? How about absolute value of x? It is differentiable in many places, but it's not differentiable at 0, for example. Must every differentiable function be continuous? Is the opposite true? If it's differentiable, must the function be continuous? And the answer to that is yes. If g is a function from a to the reals, and if it's differentiable at a point c, then g is continuous at point c. The proof isn't long. Let's take a look. By hypothesis, we are assuming that this limit exists. That's the g prime of c. Here's another limit that clearly exists. The limit is x goes to c of x minus c, and that value is just 0. And now consider this. the limit as x goes to c, g of x minus g of c. What I'll do with this expression is I'll divide by x minus c and I'll multiply by x minus c. So that's where this first equality comes from. I've just divided and multiplied by the same amount. But now I have two expressions, and these are the two limit expressions that were shown earlier. So I can take the product of the two limits, and I get g prime of c times 0 equals 0. And so this equality comes from the algebraic limit theorem for functional limits. If two limits both exist, then the limit of their product is the product of the two limits. And then it follows that as x goes to c, g of x turns into g of c. So in other words, what does this exactly tell me? My function g is continuous at c. So if it's differentiable at c, it has to be continuous at c. We've seen theorems like this one, the algebraic differentiability theorem, in a variety of contexts now. We saw it for sequences, we saw it for functional limits, we saw it for continuity, and now we have it for differentiability at a point. We see the sum rule, the constant multiple rule, the product rule, and the quotient rule. For homework, you are asked to prove 1 and 2. For right now, let's take a look at 3 and see a quick proof of how the product rule works. So, ignoring the limit momentarily, we want to take a look at this quotient, fg of x minus fg of c divided by x minus c. I've rewritten that same fraction again, just left a lot of space in the middle. And now, here's the trick. I'll fill the middle by subtracting and adding the same thing. Let's break this fraction up into two fractions at the plus sign, so I'll put my denominator on both sides. And on the left, I can factor out an f of x, and on the right side, I can factor out g of c. Now look what happens when I take the limit as x goes to c, both sides. On the left, that just turns into the derivative of the product. And on the right, we end up with f of c g prime of c plus g of c f prime of c, and that is the product rule. Alright, not too bad. Let's take a look at the chain rule. The chain rule is not one of the 4 parts in the algebraic differentiation theorem, but its proof isn't too bad either. Here's a short version of the proof. The derivative, g of f at a point c, is the limit as x goes to c, g of f of x minus g of f of c over x minus c. So I'll split this first fraction up into 2 by dividing by some amount and multiplying by that same amount. So I haven't actually changed the problem. Then I have 2 limits, so the limit of each of those, the first one is g prime of f of c, and the limit of the second is exactly my f prime of c. And that looks like the chain rule. But there is a problem. Do you see what the problem is? The problem is that the limit of a product is a product of the limits rule only works if both limits exist. Now, we know that one of those exists. That this limit as x goes to c, f of x minus f of c over x minus c, that's just f prime of c. And by hypothesis, we know that f prime of c exists. But what about this first factor, this first limit? Conceivably, that limit doesn't exist if f of x equals f of c for infinitely many values as x approaches c. In fact, this will be the case with the g2 function. g2 of x equals x squared sine x as x goes to 0. And so that denominator for infinitely many values as x approaches c becomes undefined. And so this value, this whole fraction, never actually approaches any particular value. Well, the book does provide a proof that avoids that trouble. I'm not going to go through the details here on the slides, but I do invite you to open the book, take a look at that thing, and just see how different it is from the little proof up there and the extra steps that need to be taken to avoid that difficulty. Alright, continuing on. The interior extremum theorem. This is a great theorem. This is a kind of theorem that drove calculus. This is the theorem that's needed for all of our applied optimization problems, finding the max or min in an interval. Let f be differentiable on an open interval, a and b. So here I'll draw one on the picture. And if f attains a max or a min value at some point c, then f prime of c equals 0. So my c in the picture might be about there. And if I took a derivative at c, I would find that the value is 0. Now, this theorem is easy to confuse with the extreme value theorem, which we covered earlier because they both have the word extreme or extremum in them. But these are very different theorems. I want to just take a second to compare and contrast. The extreme value theorem said, if I have a continuous function over a compact set, then the function attains its max and min values. But notice, for the interior extremum theorem, by hypothesis, I'm attaining a max or a min. It's not part of the conclusion. It's part of the hypothesis. So it is opposite in that sense. Also, this new theorem, the interior extremum theorem, has a lot to do with differentiability. By hypothesis, we assume the function is differentiable, and my conclusion says something about the value of a derivative. Derivatives play no role in the extreme value theorem. And then lastly, the extreme value theorem takes place over a compact set, whereas for the interior extremum theorem, I'm starting over an open interval. So once again, I just want to emphasize, even though both of these theorems have the word extreme in them, they are very different theorems. So don't get those two confused. How about a proof? This section of the book is nice because there are several deep proofs, but none of them are really very long. So how about a proof for this one? Suppose that f has a maximum at c. I can construct a sequence xn that approaches c, and a sequence yn that approaches c, where all my x's are less than c and all my y's are greater than c. Now, we can do this because c is in an open interval. That's why that's part of my hypothesis. Well, what's going to happen? Let's take a look at this fraction, f of yn minus f of c over yn minus c. That represents a slope. And since c is a maximum, this tells me that that slope has to be less than or equal to 0. And what about if I connect on the other side? F of xn minus f of c over xn minus c. That fraction represents a slope. And that slope must be positive, or possibly 0, but certainly not negative. Now, taking the limits of each of those produces f of c. And on the left side, this has to be less than or equal to 0. On the right side, f prime of c is greater than or equal to 0. I have to conclude that f prime of c actually equals 0. So there it is. Last theorem, Darboux theorem. In this case, let's suppose I have some points a and b, and I have a function that has a derivative at a, maybe by a picture, f prime of a looks like it's maybe about 2, and f prime of b looks like it's maybe about -1. The claim is that every value between 2 and -1 has to be obtained someplace as a derivative. So for example, let's just pick the number 0.8 randomly. There must be some point on this curve where the tangent line has a slope of 0.8. Here's the official statement of the theorem. If f is differentiable on the closed interval from a to b, and if alpha is strictly between f prime of a and f prime of b, so at the picture alpha is my 0.8, then there is some c in the open interval between a and b such that f prime of c equals alpha. My c would be about there, and f prime of c equals alpha. This is really an intermediate value property for derivatives. Now we saw in 5.1 that there was a function where the derivative was not continuous. This is really interesting. I know that my derivatives might not be continuous. But even though my derivatives might not be continuous, they still have this intermediate value property. That's a little interesting. And here's a proof for that. Let's assume that alpha is strictly between f prime of a, f prime of b, and we'll assume f prime of a is less than alpha, and that's less than f prime of b. Let's make a new function g, and the reason we do this is to simplify the proof. So my new function g is f of x minus alpha x. Well, g is differentiable, and I can take its derivative. G prime of x is f prime of x minus a. And now we can see what happens when I plug in a and b into g. The g prime of a will be less than 0, and g prime of b will be greater than 0. And so we've simplified the question. Can I show that there's a c so that g prime of c equals 0 for some c in the open interval? And just, by the way, if I can do that, if I can find such a c, then I'll come back to the expression for g prime, and I will notice that g prime of c, oh, well, that was just 0, right? So 0 equals f prime of c minus alpha. Oh, so in other words, f prime of c equals alpha. So if I can solve this problem for g, then I've solved the original problem for f. Well, there's only one line left on this slide. How can I do it? Oh, and there it is. Remainder of proof is a homework problem. So for one of your homework problems, you can complete the proof for Darboux's theorem. And that brings us to the end. There is your homework assignment, and there is a little extra credit bonus problem if you'd like to try. Good luck with that. Think carefully about these ideas. There are some interesting consequences of differentiability. And as always, ask questions if you have them. I'm really happy to meet during office hours, or anytime really, and make sure that you're thinking all right on these problems, that I can answer your questions. Okay, take care. Bye.